the universe has always been one of the most captivating mysteries for humanity. Throughout history, we've gazed at the stars and wondered about the vastness of the cosmos, its origin, its structure, and its eventual fate. With every advancement in technology, our understanding has grown, but so too have the questions. And now, something extraordinary is unfolding before us, shaking the foundations of what we thought we knew about the universe. Thanks to the James Webb Space Telescope, JWST, the scientific community is finding itself on the edge of a revolution. This next-generation telescope, launched with the goal of uncovering the secrets of the early universe, has delivered results so startling that it's forcing scientists to reconsider everything, from the age of the universe to the very forces that drive its expansion. What does this mean for our understanding of the cosmos, and can science keep up with the new discoveries that are changing everything? In recent months, the JWST has revealed startling insights into the distant reaches of space. With its unprecedented capabilities, the telescope has begun to challenge long-held cosmological theories. For example, it seems that the universe is much older than we initially thought, suggesting that galaxies may have formed much more quickly than our existing models predicted. This discovery alone is enough to rewrite a significant part of the scientific narrative surrounding cosmic evolution. But that's just the beginning. The results from the JWST are also calling into question the fundamental principles we've used to understand the universe, such as the assumption that it is isotropic, meaning it appears the same in every direction. Even more alarming, these findings raise doubts about the very existence of dark energy, which has been an essential component of modern cosmology for decades. As the revelations pour in, one question emerges more forcefully: have we misunderstood the universe all along? One of the leading figures in this new era of cosmic discovery is Adam Rees, a Nobel Prize-winning astrophysicist. Rees has spent much of his career studying the expansion of the universe, and his work, particularly with supernovae, has provided some of the most compelling evidence for the universe's accelerated expansion. Rees and his colleagues, as part of the High-Z supernova search team, were instrumental in the groundbreaking discovery that the universe is not just expanding, but accelerating in its expansion. This discovery, which earned Rees a Nobel Prize in Physics in 2011, challenged the prevailing notion that gravity would eventually slow the expansion of the cosmos. Instead, they found that something, later dubbed dark energy, was pushing the universe apart at an increasing rate. This finding was a game-changer in cosmology, altering our understanding of the universe's structure and destiny. Rees has always been cautious in his approach to new theories. He knows that science is constantly evolving, and that the truth is often far more complicated than it seems. But the discoveries made by the JWST have left even him astonished. These findings suggest that many of the models we've relied upon for decades may be fundamentally flawed. For instance, the rate of expansion that Rees and others observed through their study of Type Ia supernovae no longer seems to align with current observations of the distant universe. This discrepancy is just one example of how new data is pushing scientists to rethink old assumptions. If the universe is expanding at a faster rate than expected, and if the galaxies are forming much more quickly than previously thought, could it be that the entire framework of cosmology is built on a house of cards? One of the most significant implications of these discoveries is the challenge to the concept of dark energy. Dark energy is a hypothetical form of energy that is thought to be responsible for the accelerated expansion of the universe. According to current cosmological models, dark energy accounts for about 68% of the total energy content of the universe. Yet, despite its dominant role in the expansion of the cosmos, we've never been able to detect it directly. Instead, dark energy has been inferred from observations of distant supernovae and the large-scale structure of the universe. But as the JWST continues to deliver data that contradicts some of our most fundamental assumptions, scientists are beginning to question whether dark energy even exists in the way we've imagined it. The new observations are beginning to show that the universe may have expanded more rapidly, or may have originated earlier than previously believed. These revelations cast doubt on the very nature of dark energy itself. If the universe's expansion isn't driven by dark energy, then what is causing it to accelerate? Is it possible that we've been barking up the wrong tree for decades, clinging to a theory that was convenient but ultimately misguided? The JWST's findings have provided a level of detail and clarity that was previously unimaginable. As the telescope peers back in time to observe galaxies as they appeared billions of years ago, it's revealing structures that seem far more mature and developed than current models would suggest. This raises the possibility that the universe's evolution has unfolded in ways we didn't anticipate, and that our theories about dark energy, and perhaps even the expansion of the universe itself, need to be reconsidered. While these discoveries are undeniably exciting, they also present a daunting challenge for the scientific community. Rees, along with other cosmologists, has expressed concern that our current models are simply inadequate to explain the universe as it truly is. What happens now, in the wake of these unsettling discoveries? Are we on the brink of a complete overhaul of our understanding of the cosmos, or is this just another in a long line of scientific hiccups that will eventually be smoothed out with more data? The truth is that we simply don't know yet. What's clear, however, is that the universe is far more complicated, more mysterious, and more beautiful than we ever imagined. And as we peel back the layers of the cosmic onion, we're bound to find that the answers we seek may be more elusive than we ever thought possible. The revelations from the JWST have also sparked a renewed interest in some of the most fundamental questions in physics. If dark energy is not the answer, and if the isotropic model of the universe is in doubt, then what are the forces at play in the cosmos? And how do we reconcile the world of the very large, the vast galaxies, the sprawling universe, with the world of the very small, the particles that make up matter itself? This question has long been a source of tension in modern physics. On the one hand, quantum mechanics offers a detailed and highly accurate description of the behavior of subatomic particles, but it struggles to explain the large-scale structure of the universe. On the other hand, general relativity, which describes the behavior of large objects like planets and galaxies, cannot fully explain the strange phenomena we observe at the quantum level. How do we unify these two seemingly incompatible theories into a single, coherent framework? This is where the work of theoretical physicists like David Gross becomes crucial. Gross, another Nobel laureate, is an expert in the theory of strong interactions and string theory, which aims to reconcile quantum mechanics and general relativity. Gross believes that the answers to the universe's deepest mysteries may lie not in the cosmos itself, but in the fundamental particles that make up all matter. By understanding the behavior of quarks, the building blocks of protons and neutrons, scientists may be able to uncover the forces that govern the universe's expansion and evolution. Gross's work on asymptotic freedom, which describes how quarks behave at extremely high energies, has already had a significant impact on our understanding of the early universe. This is the very period when the universe was hot, dense, and filled with particles that had yet to form into the familiar atoms and galaxies we see today. Gross, however, isn't the only scientist pushing the boundaries of our understanding of the cosmos. The work of physicists exploring quantum fluctuations and the cosmic microwave background, CMB, is also shedding new light on the early universe. The CMB is the faint radiation left over from the Big Bang, and it provides a snapshot of the universe just a few 100,000 years after its birth. Scientists have studied this radiation for decades, and it has provided some of the most compelling evidence for the Big Bang theory. Yet, as new data emerges, some researchers are starting to question whether the CMB could also offer evidence of something even more profound, like the existence of parallel universes or a multiverse. While the existence of parallel universes is still purely speculative, the idea that the CMB could provide evidence of other universes has captured the imagination of scientists and the public alike. The CMB is filled with tiny fluctuations that reflect the conditions of the early universe, and these fluctuations could potentially provide clues about the nature of the cosmos, including the possibility that our universe is just one of many. Some researchers believe that the data from the CMB could be interpreted as evidence of collisions between our universe and others. If this is true, it would suggest that the universe is far more complex and interconnected than we ever imagined. At the end of the day, the universe is full of mysteries, and the work of the James Webb Space Telescope is only beginning to reveal them. As scientists continue to process the data and make new discoveries, we are likely to face even more questions about the nature of the cosmos. While these discoveries may seem unsettling, they also present an incredible opportunity to revise our understanding of the universe. We are standing at the edge of a new era of exploration, one where the questions are as important as the answers, and where the mysteries of the universe are waiting to be unraveled.